Welcome to the Newton's Laws tutorial. In this tutorial, I'm going to discuss the 3 laws of motion that were put forth by Sir Isaac Newton. We talked about him in the last tutorial as the guy who first described how gravity works, and he really didn't explain it. He didn't have a theory of gravity. He just came up with laws that described how gravity was operating. He also came up with laws that were more general about motion in general. And these things sound really simple, and yet there are many misconceptions that people have about motion. And we'll talk about those as we go through the 3 laws. The first law is called the law of inertia, and we'll discuss the word inertia in a little bit. But before we do, I just want to familiarize you with this law. Here's the technical language that describes it down at the bottom. An object in motion stays in motion until acted upon by a force. An object at rest stays at rest until acted upon by a force. This is kind of common sense. You know that it takes a force to move something, and if something is moving already, it takes a force to stop it. Here's a classic example of Newton's first law. We roll the cart down the ramp into an obstacle, and the blocks that are inside of it fall out because after the cart is stopped, the blocks keep going. They keep going forward because there's no force stopping them from moving. The cart was stopped, but not the blocks. This is the basic idea behind why we have seatbelts in cars. Because the same thing happens if you and the car are both traveling at 60 miles per hour and somebody slams on the brakes. Well, the brakes are attached to the car, not to you. So the car stops, but you keep moving forward. The seatbelt is there to attach you to the car so that you slow down as the car slows down. We saw 2 really good examples of inertia on the roller coaster. The first place where we saw inertia, you probably remember. Take a minute and pause the tutorial and see if you can pinpoint the spot where we saw the marble that was attached to our cart, or not really attached, just sitting in our cart, where we saw that marble behave according to Newton's first law. Hopefully you remember that it was over here. Remember what happened there? When the cart reached that point, the track bent, and so the cart followed the track. It went this way. But the marble, which wasn't attached to anything, went that way because that was the last direction it was going in. That's inertia. That's Newton's first law. The other place that it's not so obvious that inertia is happening is right here. When the marble is there, the last direction it was moving in because of the shape of the track is that way. So that marble has a tendency to move up here, which is why that marble doesn't fall out. Because when the cart gets up here, you might think, oh, gravity's going to pull that marble down. Yes, it is. But inertia is pushing it up. It was last traveling in an upwards direction. And it will eventually, its inertia will be changed by the fact that the cart is going to kind of push it. However, it has to catch up to it. So while it's going around the loop, it temporarily is sort of stuck, that marble is stuck to the cart in an upside down position. I demonstrated this also with a bucket of water, that I could spin the bucket of water overhead and the water wouldn't fall out because inertia keeps the water pinned to the bottom of the bucket because that bucket keeps changing direction and the water keeps trying to go in the previous direction that it was last going in. In order to really understand inertia, we first have to understand these other 2 words, mass and weight. Because most students confuse mass with weight, and that's because on the planet Earth, if you're not a scientist, you kind of think of them as being the same thing. To help you understand the difference, I want you to think about a ballerina and a football player. You know that traditionally, the football player would weigh a lot more than the ballerina. And you probably also think of the football player as being more massive, and that's true. The football player has more mass and more weight than the ballerina. But weight is something you can only have in a gravitational field. So if you're on the Earth or near the Earth, or even if you're on the moon, you will have a certain amount of weight. You'll have less weight on the moon than you do on the Earth because there's less gravity on the moon than there is on the Earth. And so the pull of the moon on the particles in the bodies of the ballerina and the football player is less than it would be on Earth. However, the mass of the football player and the ballerina never changes no matter where they are. The mass of the football player and the ballerina has to do with the number of particles that make them up. And that's one way to define mass. So one definition of mass is the amount of matter in a substance. But in physics, we prefer this definition. And what we say is that mass is the same thing as inertia, and that the definition of mass and inertia is as follows. It's the tendency to resist changes in motion. That's what mass and inertia technically are. So, which of the two people resists the change in their motion more, the ballerina or the football player? Think of it this way. Who would be easier to push? Or who would you rather have tackle you? If you want to push these two people, the football player is more massive. He has more inertia. It's harder to get him to start moving. That's the kind of change in motion we're talking about. Likewise, if the football player and the ballerina are both charging at you, going to tackle you, you want to be able to stop them. It would be a lot easier to stop the ballerina than it is to stop the football player. And it's also easier to change the direction of the ballerina. If you wanted to swing her over your head like you do with little kids, right? Whee, over your head. You're not going to do that with the football player because it's going to be really hard to get him to change direction. But it's much easier to get her to do it. So inertia and mass are defined as the tendency to resist changes in motion. All mass resists being moved around or stopped or resists having its direction changed. Okay, so now let's talk about Newton's second law of motion. It's an equation, F equals ma. The letter F stands for force, the letter m stands for mass, and the letter a stands for acceleration. The formula is important, and we're going to work with the formula a little later in the course. But right now, I want you to just think about what the meaning of this formula is. And here's the meaning. You know instinctively that if you want to push these two shopping carts, you're going to have to push one of them harder than the other one to get it going. Which one will you have to push harder? Well, I hope it's obvious. It'll be this one. That's because it has more mass. What this formula says is that the acceleration that is caused by a force depends on the mass. So something that's more massive requires more force to be pushed at the same acceleration. So if I want to accelerate these two shopping carts, I need more force on the heavier one, on the more massive one, and less force on the less massive one. It's very common sense, right? Heavy things need more force to be moved than lighter things do. So there's no tricks in that one. The third law is a little bit confusing. Newton's third law is called action-reaction, and here's what it says down at the bottom. For every action, there is, not this is, for every action there is an equal but opposite reaction, and forces occur in action-reaction pairs. Here's what happens. If this girl's on a skateboard and she pushes against the wall, her push is in this direction, but the wall pushes back in that direction. If that weren't happening, she wouldn't move, and you know that she would. She would push off against the wall. It's the normal force that's actually pushing her backwards, right? So she puts a force on the wall, and the wall gives her an equal push in the opposite direction. Those two forces are called an action-reaction pair. Action-reaction pairs occur on different objects in opposite directions. So she's putting a force on the wall in the rightward direction, and the wall's putting a force on her in the leftward direction. All forces come in pairs. So we could also talk about the action-reaction pair down by her feet. Gravity's pulling her down, and you might think, oh, wow, that's right, Mr. Kuzi, the normal force is pushing her up, except no. Actually, gravity's pulling her down, so the earth is pulling her down, and believe it or not, she has a gravitational pull on the earth that is equal to the amount of pull the earth has on her. And you might think, well, wait a minute, that doesn't make any sense. That would mean the earth would be moving towards her. But it wouldn't, because the forces are equal to each other. They're in opposite directions. She's pulling on the earth with about the same amount of force that the earth is pulling on her, and that's about her weight. Her weight being pulled on the earth is not very much force, so that's why the earth isn't responding. But those two forces happen in pairs, equal and opposite to each other. So action-reaction pairs are probably one of the most misunderstood things in all of physics. So we'll talk a lot more about them because it's easy to get confused, right? You have to realize that for every action there's an equal but opposite reaction, but the two things are happening on different objects. So we'll get confused about it, and then I'll get you unconfused, and we'll work our way through it. So those are Newton's three laws. They are simple, but they have a little bit of trickiness to them. So for your quiz, what you want to do is you just want to focus on being able to remember what each law is basically about. So if I were to show you a picture of each one, you could tell me, oh yeah, that's the first law. Oh, that's the second law. Oh, that's the third law. And that's really all I want you to be able to do right now. And we'll develop that much more when I see you guys again in class. Okay, see you then.